Right. So the next speaker is Patrick Oare to tell us about low-lying spectrum of two-dimensional n equal to adjoint QCD from the lattice.
Yeah, great. Thank you for the introduction, and thanks for the invitation to talk here. So I'm going to be talking about some work that I've been doing with my collaborators here, trying to compute the low-lying spectrum of two-dimensional adjoint QCD from the lattice. I realized I should have been more specific in this title and said that this is from Euclidean lattice Monte Carlo, considering Ross had that great talk earlier about computing the spectrum from Hamiltonian methods, but it would have been way too long because it's already very long. Adjoint QCD is a well-loved topic by this collaboration, and it's a great toy model for studying confinement. So it was introduced in the 90s, and there's been a lot of talks about this specific model over the years. It's the theory of a Majorana fermion coupled in the adjoint representation to an SUN gauge field with this Minkowski action here. So psi is our Majorana fermion field, which has adjoint indices. G is our gauge field. And the theory confines when the Majorana fermion is massive, but then, interestingly enough, when the Majorana fermion is massless, it deconfines. We're going to be studying the case when the Majorana fermion is massive, just because we're doing a lattice Monte Carlo calculation. So those have trouble when the fermions become massless. And yeah, there was a really interesting talk by Ross earlier, which computed the spectrum, or which talked about computing the spectrum of the theory using a lattice Hamiltonian approach. Specifically, I guess, for n equals 2 and 3. But the Princeton group has also done a lot of great work using DLCQ to calculate the spectrum for n equals 4 as well. And then the spectrum has also been studied in as n goes to infinity in the 't Hooft limit. From the lattice gauge theory perspective, or from the lattice Monte Carlo perspective, the first study was published earlier this year in this really nice paper by Jörg Bergner, Stefan Piemont, and Matat Unsal. So they studied a number of different gauge observables for the theory using two different discretizations, a Wilson discretization and a reweighted overlap discretization. This talk is just going to focus on a standard Wilson discretization, although we're hoping to extend this to actions that have better chiral features like overlap and domain wall shortly. But right now we're just looking at this with a Wilson discretization, which has the following Dirac operator. It's not too important, the exact details of the Dirac operator, other than the fact that, yes, our Dirac operator does not really have chiral symmetry, which we hope to fix in the future. We are currently we have not generated a lot of very large lattices, so we're more, we have a lot of kind of small lattices, so ranging from 10 by 10 to 28 by 28. In which we're trying to just develop the methodology and look at the spectrum on these small lattices before eventually generating larger ensembles and then taking continuum limits. I started this ensemble here because most of what I'm going to be showing you is computed on this 20 by 20 ensemble. So we've not yet taken any continuum limits. So it's all at finite lattice spacing. I should also emphasize this is all very preliminary work. And we're going to be increasing the scale of the calculation soon. Before I talk about any of the specifics of the calculation, I do want to make a comment about simulating Majorana fermions using lattice Monte Carlo, in that we're trying to evaluate the path integral here. When you have a Majorana fermion instead of Dirac fermion, and you integrate the fermions out, you get a Pfaffian of the fermion Dirac operator. Now that Pfaffian is not guaranteed to be positive, and in fact it can be negative. And since we're effectively, if you want to include dynamical fermions as a calculation, we're sampling from this probability measure. If that Pfaffian is negative, it provides some real issues for simulating the theory. In particular, if you can prove this Pfaffian is always positive, that's the best case scenario. You can then always use a lattice Monte Carlo calculation to simulate the theory. But even in the case when it can be negative, you can reweight the probability measure. And essentially you can sample from a distribution that has the norm of the Pfaffian here, which is guaranteed to be positive, and then absorb the phase of the Pfaffian into whatever observables you're computing. So in our case, we looked at the norm of the phase of the Pfaffian on each of these configurations that we're computing, and we've seen that it's so far been real and positive, which indicates there's no sign problem that we have to worry about. But this is not, in general, an exhaustive proof. So there are a lot of ways to extract the string tension from lattice Monte Carlo. And we're simply computing all possible Wilson loops on each configuration that we sample, and then extracting the static quark potential by looking at the large Wilson loop limit, and extracting the string tension by fitting a linear ansatz to this potential. So again, these are all data points from the 20 by 20 ensemble that we generated. Looking specifically at spectroscopy, spectroscopy from the lattice is, extracting the ground state is generally reasonably easy, but extracting excited states is, you have to be a lot more careful. And on the lattice, we're working with a discrete spectrum, and each state, I shouldn't have said defined, I should have said is characterized by its quantum numbers. So each state is characterized by its symmetry properties, by its symmetry properties under the different symmetries of the system. So like parity, isospin, and all that. And how we extract the spectrum is that we find an operator that has the specific quantum numbers of the states of interest, and then we compute correlation functions of those operators. So here Z is going to denote this, there shouldn't be a T there, but they should denote this matrix element here. And we take some operator with the relevant quantum numbers of of the states of interest, and we compute the 2-point correlator here. So we excite some states, and then we annihilate it at the sink. You can spectrally decompose this, and the 2-point correlator looks like a tower of decaying exponentials. And the idea of lattice Monte Carlo is that you can extract the ground state dependence, or you can extract the ground state of the system by analyzing this and looking at the large T limit, because all of the excited states here will die off, and so you'll only be left with contributions from the ground state. The reason this is hard is because the reason why this is hard to extract excited states is because if you're trying to look at terms here that are not the ground state, these also die off very fast. So you have to be very careful. Specifically for this project, we're looking at Dirac bilinears. So we're going to look at operators of this form. So it's psi bar, or it's a gamma structure sandwiched between a psi bar and a psi projected to definite momentum. And we're computing these 2-point correlators here. Now, we expect the identity in gamma 1 to excite scalar states, so even parity states, and gamma 5 and gamma 0 to excite pseudoscalar states, so odd parity states. And then what we're working on now is we're trying to we're trying to do a variational analysis for the excited states of the system. So if you actually enlarge your operator basis, you can compute essentially a matrix of correlators here and then solve the generalized eigenvalue problem to give yourself variational bounds on the nth energy levels of the system. So I'll show some results from this, but I'm not going to talk too much about the specific details of how this works. So looking at the 2-point correlators that I just discussed, this is kind of what you conventionally expect to see from a lattice calculation. I don't want to shut this computer down. All right, thank you. So this is the pseudoscalar sector, plotted on a log scale. So this linear trend on a log scale indicates that we're seeing an exponential decay of these correlators. If you look instead of the scalar sector, things look a lot different. So instead of having a nice exponential decay here, you end up, the scalar sector ends up plateauing to a constant value, which indicates that essentially these scalar operators are interacting non-trivially with the vacuum. So a little bit more care has to be taken into extracting the scalar energy levels, and we're currently working at that. Looking at the pseudoscalar sector, I'm just going to go a little quicker. You can take the log difference of the correlator to create an effective mass plot, where essentially the plateau value of this effective mass plot is the ground state energy of the specific sector you're looking at. So here, the plateau value is about 1.6 for the 20 by 20 ensemble. The exponential decay here at low times contains all the information about the excited states of the theory, which we're hoping to extract with the GEVP. So yeah, again, talking about the GEVP, this gives you variational bounds on excited states of the theory. These are apt to change if you add in more operators and you look at a larger operator basis for your theory. Great. And essentially, we're still in the process of actually computing specific numbers for the higher energy states of the theory, because you need to make sure that these things are stable if you add additional operators. So this is still very much a work in progress. The last thing I want to comment on is that you can add 2 additional operators to the theory. There's this really nice paper by Alexei where he talks about 4 fermion deformations of adjoint QCD. And certain discretizations of the adjoint QCD action can potentially radiatively generate these operators, and you can actually explicitly compute the expectation values of these operators to see if you're simulating this, if our lattice simulations of the theory are generating these 4 fermion couplings. So we've computed the correlation, we've computed this matrix element of O1. And we've seen on all of our ensembles that, in fact, this expectation value is non-zero. And I guess, I'm basically out of time here. So I'll wrap up with this, that we're hoping to do a more in-depth analysis of this and determine, exactly what the values of the couplings that are being radiatively generated by our lattice action are. Thank you.
So which value of the mass are you using in the results, and can you take also large or small masses?
Yeah, so you can. So right now, all the masses are in lattice units. And I guess comparing to like a general value of the mass is kind of hard, just because it's not a physical theory. So any scale setting, any matching to a physical theory doesn't really exist. But you can compare within different ensembles that you've generated. So it's I want to give you a better answer and say, we used a mass of 1 GeV for the fermion.
And your short mass related to string tension.
So we're setting the scale with the string tension, which I think I have. It's kind of everything's related to the string tension here. These are our calculated values of the inverse of the string tension, so which we're going to use to set the scale. Exact numerical values are.
At some point, your string tension may go to 0. Everything is good.
Mitad?
Can you go back to your last slide?
This one?
If the last item is correct, that would be very interesting. I mean, if it survives in the mass goes to 0 limits, that would mean that, at least in this regularization scheme, we cannot really think of QCD adjoint as just, massless theory. We have to think in the existence of this for Fermi, and that becomes a confining theory. Of course, it also means that that particular regularization scheme does not respect non-invertible symmetry, because non-invertible symmetry actually forbids that operator. But this is, to me, this is super interesting.
And I think we're planning to investigate this a little further, and especially like where it flows, and as you're actually looking on these ensembles, because I mentioned this is just specifically on one ensemble, even though we've computed a couple of them, just because we're still trying to play with the continuum limits that we're taking and make sure that we're on a trajectory that we understand well.
Ross said that this would be suppressed by the lattice scale.
So looking at the across the different lattice scales that we have, it does not seem to go to 0, which was surprising to me, and which is why we're still investigating this, because we would hope that.
Where did that criterion come from? I don't understand it.
Why
is the web indicating its presence in the action?
Why?
Yes, it's obvious. Oh no.
Not to me.
Okay.
Let me see. I can't do the detailed explanation off the top of my head, but I can. It's in Alexei's in Maria's paper.
I can make an argument for why it's true in the massless point.
But
I don't see why it's true in the massless point.
You are at finite mass.
We are at finite mass.
You really want to take mass to 0 and 8 to 0. And then
in the massless
okay, so
limit, in the massless limit there's a one-line proof. But in the massive, I don't understand.
Okay, let me. So.
Just a more basic question. It seems like since you're taking only bilinear operators, you're only studying bosonic states. Right?
Yes.
But I think the lightest state with the smallest gap is fermionic state.
Yeah, so we have to change our operator basis for that, which we are doing at the moment. So yeah, so right now, unfortunately, we're limited, to a very small subset of the actual states that are in the theory.
So you can't compare yet with the mass
Yeah,
that were found using the LCD.
yeah, not yet, but that is our eventual goal.
Any other questions? If not, let's thank Patrick again.